Okay, we're going to pick up here where we left off, and we're going to talk about still um, measurements, significant figures. What we were talking about again, we were talking about our sig figs, and we were talking about again what constitutes sort of a significant figure. A reminder again, any non-zero is going to a non-zero, I guess should be good, is going to be significant. Remember that we also have zeros. So there is the leading zero that is not significant. Again, it's just sort of a placeholder there. So no matter how many you got going on there, it will not be a significant figure. Remember, we go left to right, and we don't start counting until we hit the very first non-zero number, which in this case would be a 3. And then the rest of the numbers here would also be non-zero. So this guy would have 3 significant figures in this case, being these guys. We have sort of trapped zeros or captive zeros, and those are going to be significant. They are trapped between two non-zero numbers. So here again, we would start counting at the 3. Those two would be significant, and this guy would be significant as well. So that guy would have 4 significant figures. And lastly, the 0 that really gives people sort of the hard time going to be that 0 at the end, or the trailing 0. And those has to do with decimal places, decimal points. So remember that if you do have a decimal point in your number, it will be significant, those zeros that come at the end. It doesn't matter if the decimal point is near the zeros or not. It just has to be in the number. So that's the only thing that it has to be for it to be significant. Again, 0.00400. We don't start counting here. That is where we start counting. These zeros, once again, going to be significant because there is an actual decimal point written in the number. So this would have 3 significant figures in this case. Now, again, if we wrote 400 like so, we would have just our 1 significant figure there. There is no decimal point. So when trying to decide significant figures or not, we do not assume that there's a decimal point there or anything. It does need to be actually written into the number. We talked about calculations using significant figures. And when we multiply and divide, we are looking at significant figures, and it is the least. So again, the number that has the least number of significant figures in whatever calculation you're doing is how many significant figures your answer should have. And remember that if we kind of add and subtract, it's a little bit different. We are looking at decimal places, and it's also the least. So the least number of decimal places is how many decimal places your answer should have. Remember that that also will give you a certain number of significant figures if you go to decimal places, which might be important if you continue on with that number and use it in another calculation. You do need to watch out for things like calculations, and if you're doing multiple steps, you want to keep track of the significant figures and stuff throughout your calculation, but you really don't want to kind of round a lot until the very end. Remember that if you round a little bit here, round a little bit there, you might find yourself far away from the true answer versus where it should be. So it's always good to keep a couple guard digits. Don't round too much. If you have a calculator and you're still kind of using the number in the calculator, just use the whole number, but you should still keep track of it throughout the sort of calculation along the way. Any questions on any of that stuff there that we talked about last time? All right. So let's look at some of these examples. Why don't you take a few moments, and for each of them, why don't you give the proper... Okay, so let's take a look. And again, a good reminder that your calculator does not always spit out to you the right answer in terms of significant figures and how you should report the answer. So again, if we got that on our calculator here, we're multiplying. So we are going to look at significant figures. And our first number here's got 3 significant figures. Second number here's got 2 significant figures. So we should end up with the least, which is 2. And again, that would take us to the 3, we would look at the 7 and we would round to 9.4 in this particular case. Questions on that one there? Look at the next one. We're dividing. So again, getting this number on our calculator. Our first number here has 4 significant figures. Second number there's got 3. So 3 significant figures is going to be our winner in this case. And if we look at our number on our calculator, for example, the 8 is our third significant figure. So we would look at the 2, and in this case, it would be 0.0758. We would just drop all of the numbers there along the way. Any questions on that there? Here we're going to be adding. So when we're adding, we're actually looking at decimal places. So that's 2 decimal places. That's 1. That is 3, and that is 3. So when we look at decimal places, we are still looking at the least number of decimal places. I guess that last one doesn't count because that's the answer. So we are looking at 1 decimal place where we want to end. So that is the 1 there. The next number is a 3, so we'll just drop the rest of them and end up at 29.1. Here, 29.1 has 3 significant figures and 1 decimal place. Again, the significant figures might be important if we continue on. Lastly, here we're subtracting. That is 4 decimal places and 1 decimal place. That means we would look here. That is going to be over 5. So 0.6 would be where we would want to round. Any questions on that there? All right, so we saw this a little bit earlier. So a reminder that you pretty much do, again, need to know this. Pretty much these prefixes. Remember that what we see here are essentially 1 times those numbers, like 1 times 10 to the 6 is it in scientific notation. Also a reminder, again, if we had something, say, like kilo, which is 10 to the 3, that again is basically 1 times 10 to the 3. And you want to make sure that you do it correctly. So again, that 10 to the 3 represents how much there is in the base unit to one of the prefix units. So 1 kilometer would be 10 to the 3 meters. So again, basically 1 times 10 to the 3 meters. That is, again, the correct way to do that. Just like if we had nano here. Nano is 10 to the minus 9. That is 1 times 10 to the minus 9. You would put it in your calculator just like we talked about scientific notation. Use your exponent button. 1 nanometer is equal to 10 to the minus 9 meters. So again, you want to make sure that you do those correctly. It is, as I mentioned previously, very common that people always do that sort of conversion backwards. You want to make sure that you do it. So what we see here is how much there is in one of the prefix units to one of the base units. Again, it doesn't matter what the base unit is. In 1 kilogram, for example, there's 10 to the 3 grams. So it doesn't matter if they're grams, meters, liters. It doesn't really matter. Again, the prefix works the same way. Any questions on that there? So we talked about some length equalities, and these again are ones that we do come across, and you should know probably all of them that are here actually. And what is an equality? An equality is basically 2 values that are on different scales, but they do represent basically the same amount of whatever it is. So when we say we have 1 meter or something, that is the same as having 100 centimeters. Kind of the same idea if you had 100 pennies, that equals $1, right? They both represent the same amount of money. They're just on different units in terms of their scale. Volume, again, definitely 1 liter and 1,000 milliliters, something we see a lot. Also remember, as we'll see on the next slide, I think 1 milliliter is the same as 1 cubic centimeter. So that is a 1-to-1 conversion. We use cubic centimeters like you did with the wood block in the experiment where you did the length times the width times the height and you measured it in the lab. We use milliliters, right, a lot when we're just measuring volume and say something like a graduated cylinder, which you also did in one of those experiments as well. So when we cube a length measurement, we take like the length times the width times the height, again, each in centimeters, for example, gives you cubic centimeters, which again is a volume. So basically, if you cube any sort of length measurement, in the case of a cube, and you take that measurement and cube it, you will have talking about a volume. So you can see there, decimeter cubes is equal to 1 liter. So we definitely use that a lot. It does pop up in terms of volume. We also talked about the importance, again, when we take measurements to make sure that you do properly look at a scale. And again, here we're looking at a graduated cylinder in this case. So just a reminder that if you took the larger markings here, for example, if we look between here and here, difference is 10 milliliters, and that's our large marking. We also want to count up how many little markings we have between them. 1, 2, 3, 4, and then 5. So if we take our large markings and divide it by how many little markings we have, which is 5 in this case, we will see in this case that each of the small markings represents 2 milliliters. So that would be like 82, 84, and so forth as you continue up. Remember that it is a small marking in terms of determining what it represents, that we can also divide it by 2, and that gives us our uncertainty in that measurement, which is not that, which would be plus or minus 1 milliliter in this case. And that is what we typically would record. So, if we were somewhere between, say, the 82 and 84 mark, the best we could do on this would be 83 milliliters plus or minus 1 milliliter, with our uncertainty being in the whole digit here, this being our uncertain number, that being our certain number in that particular case. So a reminder again here, they want you definitely when you're taking measurements, especially in lab, to also include that uncertainty, that plus or minus, which is achieved by taking the smallest markings and dividing it by 2. Any questions on that there? Mass as well. Again, I would say these are important ones. 1 kilogram equals 1,000 grams, or 1 gram is equal to 1,000 milligrams. 1 milligram equals 1,000 micrograms. That's what this little symbol here represents. It's micrograms. And this brings up a really good point in terms of sort of conversions and where people sometimes make an error. And maybe we'll go back to that table there that we saw earlier. I'll just kind of erase everything that's on here. Maybe we will. There we go. So if we look at this table, and for example, let's just say that we are going from one prefix unit to the next. So let's just say we had 452 nanometers, and we want to know how many centimeters that would be, right? Now we're kind of going from prefix to prefix, and sometimes people screw up really easily by trying to figure out, well, I just kind of move my decimal this way or that way, and I'm not sure how many ways really I'm moving them. So my recommendation is, since you need to know sort of this chart, you can very easily find the conversion from one prefix to the base unit. And if we think about sort of nanometers to centimeters, really the unit that ties them together is the base unit, which is meters. Meters are in all of them. So we can very easily go from nanometers to meters and find the prefix to easily go from meters to centimeters. And that's probably a really good move rather than trying to go directly from one prefix to the next, because again, a lot of people really screw that up. So how would we do this? So for example, we would find our nano, as we talked about a second ago, which is our 10 to the minus 9. And again, that means that in 1 nanometer, there are 10 to the minus 9 meters, or 1 times 10 to the minus 9. This is again an equality, by the way. And from any equality, as we'll talk a little bit more about in just a bit here, you can actually write two conversion factors. You could write 1 nanometer over 10 to the minus 9 meters, or you could flip it around 10 to the minus 9 meters over 1 nanometer. These are what are referred to as conversion factors. They basically are just fractions. We could also do the same thing between centimeters. So centi, which is here, is 10 to the minus 2 for centi. So that means in 1 centimeter, there are 10 to the minus 2 meters, right? And again, that's an equality that we could write two conversion factors for. 1 centimeter over 10 to the minus 2 meters, or I'll go right here, 10 to the minus 2 meters over 1 centimeter. So really from any equality, we could get two conversion factors. And this helps us really do this sort of conversion a lot better than a lot of people will do when they try to go prefix to prefix. Again, you don't have the benefit of like Googling, the direct conversion and stuff like that, but you'll know these conversions. So we will set this up, and we're going to talk more about it today, but you do want to set this up what is known as dimensional analysis. And dimensional analysis is the way they want you to show work in this class. It is a place where we show the units, and we basically use fractions or conversion factors to go from one unit to the next. So we get rid of the unit we don't want, and we keep the unit that we do want. The way we do that is to make it really simple, which is a very simple thing to remember, which is opposites cancel. So if you want to get rid of some unit, you need to put the same unit in the opposite location. What are we talking about in terms of location? Top and bottom, pretty much. Pretty simple. It's either on top or it's on the bottom of that unit. You need to put it in another location. So if we were going to start with this conversion here, even though it is not written as a fraction, we could kind of think of it as being over 1, and you don't really need to write that, but if it helps you visualize it, what it helps us visualize is I could clearly see the units of nanometers. Are they on top or bottom here? They are on the top, right? So just remembering dimensional analysis is opposites. I want to get rid of nanometers. I need to find the conversion factor where nanometers are on the bottom. And if I go to my first one from nanometers to meters, the one where nanometers are on the bottom is this one right here. And that is what I'm going to use as a conversion to do this. I'm going to set it up here again, top and bottom. Bottom 1 nanometer, top 10 to the minus 9 meters. Now, math-wise, what we're doing when we set up a problem like this, which is again what's referred to as dimensional analysis, is anything that is on the top gets multiplied, and anything that's on the bottom gets divided, basically. So that keeps it also quite simple. Everybody on top gets multiplied, anything on the bottom gets divided. And what that does in terms of the units is this: the nanometers on top and the nanometers on the bottom, since they are dividing by each other, will end up canceling out. It is basically you're taking nanometers up on top divided by nanometers. That equals 1. It's the same idea if you had 2 divided by 2 equals 1. 4 divided by 4 equals 1. So you have the same units on top and bottom and you're dividing, they will cancel each other out. If you have the same units and you multiply them, they will continue to like square or cube, depending on what you're doing. So if I stopped right at this point, I could get an answer, but it wouldn't be the answer I'm really looking for, right? Because we want to get to centimeters in my example here. We're actually stopped right now, right there, halfway through. And the reason why this is a good way of doing it is now I'm in meters and I just need to go to centimeters, which clearly I could find very easily off of this table or my memorization of this table and find the conversion factors I need. Also, setting it up like this, dimensional analysis, which is the way you're supposed to set it up, we could also clearly still see that our units that I want to get rid of now are on top. So again, we need to get rid of them by putting in the opposite location the same units, which would be the bottom. In this case, we actually need meters on the bottom, which means I would want to use the conversion factor here on the left where meters are on the bottom. And if we do that there, that would be 10 to the minus 2 meters equals 1 centimeter. Meters on top and bottom again will divide out. That's going to leave me only one unit left here, and that's on top, and that is centimeters. And that's typically what you want when you do this type of calculation is if you're just looking for an answer that has one unit, that one unit needs to be on top by itself, right? So that you get the right one. So what are we going to do? We're going to multiply. So we're going to multiply everything on top. And then again, come back here and divide by what is on the bottom in this case. So if I do that, I'm going to take 452. I'm going to multiply it. And again, the 10 to the minus 9 is 1 times 10 to the minus 9. So you would put that in your calculator in most cases, just like you were going to put this number in, basically. So using your exponent button like we talked about and all that good stuff. So you're going to multiply times 1 times 10 to the minus 9. By the way, that takes care of everything that's on top. There's a 1 at the end. You don't really need to multiply it by 1 unless you want to, but you can. And you're going to hit equals. And that's really important. When you get done multiplying everything up there on top, make sure you hit the equals button. Now, wherever people screw up as well is if they have multiple numbers on the bottom that they need to divide by, and they try to put it all into the calculator at once, they screw up and get the wrong answer. So I'm going to show you how you could do it pretty much and get the right answer always. What you want to do if you have multiple numbers on the bottom, which in this case we kind of have one, so we don't have a lot of multiple numbers, but you want to divide by the first number and then hit equals, and then divide by the second number and hit equals, divide by the third number if you have 3, hit equals, and so forth. So if you have multiple numbers on the bottom that you're dividing by, I would hit equals, divide by the number, hit equals, divide by the number, hit equals, every single time you get the one. If you try to put it all in at once in your calculator and you don't do it correctly with parentheses, which most people do not, you will get the wrong answer because your calculator will break up the numbers incorrectly. So what I'm going to do in this case is I hit equals up there on top. I got something like 0.000000452. I'm going to divide by really the only number that's there, which is 1 times 10 to the minus 2. And that's going to give me an answer here of 0.0000452 centimeters, or I could do a little scientific notation, 4.52 times 10 to the 1, 2, 3, 4, 5 minus 5 centimeters. And that is really the best way to kind of go prefix to prefix is to kind of use the base unit as the intermediate, because you could very easily find these conversions here to take it from that prefix to the base unit and from the base unit to the next prefix unit. Any questions on that there? By the way, in terms of significant figures here, the other nice thing about dimensional analysis when you set it up this way is you're just multiplying and dividing always, which means you're looking at significant figures in terms of your answer. And that is the only thing that you have to look at. So in this particular case, we have 3 significant figures here. This is an exact conversion because it's metric to metric. You don't have to worry about it. It has an unlimited number of significant figures. This one also a metric to metric conversion, so you don't have to worry about it, which actually means the only number here that you have to worry about in terms of your answer is the one with 3 significant figures, and your answer should have 3 significant figures, which it does in either of those ways that you report it there. Any questions on that there? Okay, so again, I would highly recommend if you're going to kind of go prefix to prefix, take it back to the base unit, take it from the base unit to the next prefix unit, and you usually will get it right. You just want to be careful about punching those things in. Any questions on that there? Yeah. Yeah, so let me I'll do it here. I think I got it here. So basically on this one, we had 452, right? And we're going to multiply it. So then you would hit your multiplication button. Then we had basically 1 times 10 to the minus 9. So you would punch it in just like before, 1, exponent button, negative, and 9, right? So that's basically, so this is basically our 10 to the minus 9, and you can punch it in that way. Some calculators you actually don't need to actually do the 1, you could just do the exponent button. It depends on your calculator, but if you want to be safe, you could do it that way. And really that's the end of what we have up on top. We have a 1, which is not a big deal. You don't really have to multiply it by 1. You could hit equals, and then I would hit divide, and now we're going to take care of what's on the bottom. And again, we have a couple ones there on the bottom, so we really don't have to divide by ones because nothing's going to change. So this is really the only number that we have left, which is 1 times 10 to the minus 2. You hit divide, again, put it in with your exponent button, minus 2, and then obviously hit equals. And then again, it will probably spit it out to you on your calculator in decimal form with the 0.000452. Other questions on that? Now, again, it does depend on the calculator. For example, my calculator, I'd actually could just hit the exponent button and the minus 9 and I'll hit the 1. But if you want to do the 1, it should come out the same. All right, so we did that. Okay, so we just kind of touched upon it there a second ago, but let's talk officially about conversion factors and where they come from. They do come from, as I mentioned, they come from these equalities. And equalities, again, are basically two values on different scales, but represent the same amount of something. So once again, as I mentioned earlier, there are 100 pennies equals $1. That is our equality. And from, again, any equality, we could basically get two conversion factors from it. Will you use both conversion factors in a problem? The answer is no, because you'll kind of undo what you just did. So the answer definitely is no. And you just need to use whichever one basically will work for the calculation that you're doing. That's essentially what we just talked about there on this slide. So here's a table of some common equalities. And again, I would just probably say no most of the ones that are on here, since they want you to know everything, apparently. And this is really the two types of units that we talked about. There's the US units or the English units, which again, we use here. There's also the metric ones that everybody else sort of uses. And then we have some metric to US sort of conversions there in the last column. So remember that we talked about, I think last time as well, exact numbers, and we did a little bit earlier before. And exact numbers are basically gotten by two ways. It's a definition like any of these here. 1 foot equals 12 inches. 1 kilometer is 1,000 meters. So these are exact numbers. The other way that we get exact numbers are counting. So again, if you had like 3 pens on your desk, you're not going to do any type of measurement or scientific experiment to figure out how many you have. You're just going to simply count them. And when you have an exact number, they could have pretty much an unlimited number of significant figures. And what that means is when you do calculations and you come across any type of exact number, you do not need to worry about it in terms of your calculation. You kind of ignore its contribution to the answer in terms of how many significant figures you should have. The one exception to that is if you go US to US, you're good. That's an exact number. If you go metric to metric, that's going to be an exact number. It is only when we do sort of this conversion here, if you kind of cross over and you take a metric to US conversion, then you do have to look at the significant figures in that conversion factor in a lot of cases. Now, there are a few that are English to metric conversions that are considered exact numbers. This one right here is an exact number. The 1 inch is 2.54 centimeters. And here at this school, they like to use this one as well as an exact conversion, even though really it's 453.59 grams per pound, but they use this one here as an exact conversion. So if you have either of those two, you don't have to worry about the significant figures. But if you have any of the other ones, for example, here that are listed, you do have to look at the significant figures when you're doing calculations. Now, if you look at most of these, for example, there is a number, and then there's another number that's a 1. And when we're trying to figure out the significant figures on those guys, It is obviously not the one that's a 1, it's the other number there. So that 946 would represent 3 significant figures in that conversion factor, and that's the number that we would want to look at. So if you cross over from metric to English, a lot of times you do need to take into consideration the significant figures in that conversion factor. I will say, though, a lot of times, not 100% of the times, but 90% of the time, the original number that you started with, a lot of times is the correct number of significant figures for your answer, but not all the time, but a lot of times it really is. If you cross over, you do need to take a look at the significant figures. If you're doing straight metric to metric, you don't have to worry about it. Straight English to English conversion, you don't have to worry about it. The other place where you may come across a conversion factor that you should take into account is significant figures is in an actual problem. So in an actual problem, if they say something like, hey, you're driving at 25.4 miles per hour. That is not a normal conversion. That is specific for that particular problem. You would look at the significant figures in that problem of 25.4, whatever I just said there, and that would have 3 significant figures. So that's another place that sometimes you come across conversion factors within the problem, and a lot of times you do look at those significant figures in your calculations. Any questions on that there? So again, a couple of ideas here. We have our equality, and once again, our 2 conversion factors that we could get from that, 5,280 feet over a mile, or 1 mile is 5,280 feet. Once again, we're just going to use dimensional analysis to use these conversion factors like we did with the prefix to prefix conversion we just did. And we want to, again, go opposite locations to cancel out units that we don't want. Now, for example, if you were driving 65 miles per hour, that is a conversion. When you have something per something, that is a fraction. So when you're driving 65 miles per hour, that basically means in 65 miles, it's going to take you 1 hour to get there. Or in 1 hour, you could basically travel 65 miles. And again, you could use those as conversion factors there on the bottom. In this case, if you had that in a problem, you probably would want to look at the significant figures of that number again, because it's not like, 12 inches is a foot and for every situation type of thing and stuff like that. Another really common thing here, again, if you got one like $3.05 per gallon for 91, you can see how old that slide was. That was a lot of money back, by the way, when I did that. I think it was like $1 something for, regular gas. So that means for every gallon of gas you pump, it's going to cost you $3.05. Or for every $3.05, you can get about a gallon of gas, is basically the 2 conversions that you could get there. I would say in chemistry, a lot of times we do come across percentages. And percentages oftentimes are very much useful in calculations by turning them into usable conversion factors. So, for example, when we have a percentage, the best way to do that is to assume you have 100 of something, because basically the numbers stay the same, right? Because you got like 85% on your exam, you probably got 85 points out of 100, right? So everything stays the same. So if you have something like 12% body fat by body mass, we could say a little metric sort of situation. You have 12 grams of fat per 100 kilograms, 12 kilograms of body fat equals 100 kilograms of body mass, or 12 kilograms over 100, or 100 kilograms of body mass over 12. We could do a more English type of conversion in pounds. 12 pounds of fat equaled to 100 pounds of body mass. Gives us 12 pounds of body fat over 100 pounds, or 12 pounds on the bottom there over on top 100 pounds as well. So, if you had something that was a 5% by mass to mass sodium chloride, sometimes referred to as M/M. That basically means you would have basically 5 grams of sodium chloride and 100 grams of solution. Again, assuming 100 basically, or 100 grams of solution would contain 5 grams of sodium chloride in this particular case. So that's a really good way to sort of convert things into a usable type of unit. So let's talk about using these conversion factors and dimensional analysis. And again, dimensional analysis is basically the process by which we basically do these type of problems. And it is through that idea that we have some type of equality, like a unit A equals unit B equals unit C. And again, we want to set it up so that we could get rid of units. So these are all equalities. And again, we could get two conversion factors for each of these things. We could say unit A over unit B, or unit B over unit A. Over here, unit B over unit C, or unit C over unit B. So if we were going to start with A, again, we could assume that it's on top, so we want to go opposites to get rid of it. If we want to get down to unit C, and we'll set it up like we were doing there, unit A on the bottom, unit B up on top, those will cancel. Once again, we could see unit B is on top now, so opposite to get rid of it. Unit B on the bottom and unit C up on top. Those guys will cancel. It will leave us unit C. Once again, typically speaking, if you just have one unit to solve for, it needs to be up on top by itself. If you have two units, which you can have, you just got to keep track of what's on top, what's on the bottom. And again, setting it up like this allows you to just very easily see where things are in terms of top and bottom. Opposites to cancel. Once again, multiplying the top, dividing the bottom here. Why should you use dimensional analysis? Well, besides the fact that they expect you to use it here in the school and all the chemistry classes that you do, it's also really helpful because it's a very simple concept of if I set it up like this, opposites cancel, which tells me where to put things. And I know once I have it all set up, everything on top gets multiplied, everything on the bottom gets divided. I don't have to think about, in some cases, rearranging formulas or anything like that. It will kind of do the math part of it for you. In a lot of cases, if you set up your calculations using this, all you have to do is set it up so that they cancel correctly. And just all you have to remember is multiply the top, divide the bottom, and all the kind of rearranging of certain things can be taken care of for you in that sort of move without having to do it. Any questions on that there? So the general steps to doing these problems, we want to write what's given to us. Oftentimes that helps us a lot, especially if you do know some formulas, you can kind of label what things are and it'll kind of point you in the right direction of the formula. You want to write what you want to find. You want to think about what equalities will help, and you want to think about what conversion factors will help as well. And then you want to think about a path to get you to where you want to go. Now, there are multiple ways that you can get to the same answer depending on what conversions you choose. As long as you choose a legit conversion, it all should be fine, regardless of which way you go. But you can get to sort of the same answer in multiple ways. You want to set up the problem like we've been doing there, showing the units canceling with the conversion factors, and solve the problem to the proper number of significant figures, which if you use dimensional analysis will be multiplying and dividing. So you're going to be looking strictly at significant figures in this particular case. Any questions on that there? All right, so obviously here, if we want to know how many pennies there are in $3, is kind of straightforward one. There is our equality. We could go directly from pennies to dollars. We have our two conversion factors. So we'll start with what was given to us, which was $3. Again, if it helps you, you could put it over 1. And now we could clearly see dollars on top. I need to get rid of it. Dollars need to go on the opposite location, the bottom. The number there. And dollars will cancel. We're going to multiply the top, divide by the bottom, and that will give us 300 pennies in this case. This is going to be an exact number, which we really don't have to worry about it. So that's kind of the only number we got going on, which we could worry about, I guess. And that would be one significant figure. And I would not want to put a decimal point in this case because then my answer would be 3 significant figures. So we want to make sure we watch out for that. Any questions on that there? All right, so why don't you give it a try here? You go to AM, PM, get yourself a 32 fluid ounce drink of Diet Coke. How many gallons did you drink? And here are some equalities that might be helpful. Set it up with dimensional analysis with the units, and the answer is the right sig figs. Yes. Okay, so let's take a look. So once again, as I mentioned, you want to think about a pathway to get you to wherever you want to be. And again, there may be multiple sort of pathways to get you there. In this case, we could use these equalities and take us from fluid ounces to quarts. Quarts over to gallons will get us there. And again, there could be other ways that you could do it. These are our equalities. And once again, that is going to get us several conversion factors that we could use. So these are the conversion factors that are sort of available to us. We want to start with what's given to us, which is our 32 fluid ounces. Once again, if it helps you, you could put it over one. You don't have to, but just know that it's on top basically to begin with. That helps us very quickly determine that is the one I should use there since fluid ounces is in the opposite location so that they cancel. We'll go with 32 fluid ounces is 1 quart. Once again, if I stop the calculation right at this point, my fluid ounces there are going to cancel out. The only units that I am left with right now are quarts, which is better than where I started, but not where I want to end. I now can use my second conversion to get me to gallons, which is what I want to end with. Once again, setting it up like this, you could hopefully clearly see quarts are still up on top in this case, which makes my decision making pretty simple. Opposite means I need the guy on the right there to pop it on the bottom. And now I have on the bottom 4 quarts and 1 gallon. Quarts and quarts will cancel. The only unit left are gallons, which are on top, which is what I'm looking for. Once again, here we're going to multiply whatever is up on top. We're going to come back and divide by whatever is on the bottom. I again can multiply as many numbers as I want up on top. I should hit the equal button. I will then divide by the first number and hit the equal button, divide by the second number and hit the equal button, and I will get the right answer for sure if I do it that way. So if I do that, that's a 32 basically times 1, which you don't necessarily have to multiply by, times 1. Hit equals, divided by 32 on the bottom, hit equals, divided by 4 on the bottom, hit equals. Gonna get us an answer here of 0.25 gallons. And that is the answer. 1/4 makes me think you're too lazy to divide. Yeah, so don't leave an answer as a fraction. You need to give it as a number, as a decimal, whatever it may be. Not a terrible example, but I've had people write, 445 miles over 366 hours. Looks good. Don't do that. Yeah, so divide it out, get one number at the end. Don't leave it as a fraction. We do need to look a little significant figure-ish, right? So a little exact number there. Don't worry about it. Exact number, that means right there, 2 significant figures. And I did all right. It looks like I got 2 significant figures there on my answer in terms of this one. Once again, setting it up like this, which is dimensional analysis, all we're doing is multiplying and dividing. So we're always looking at significant figures in that case. And the least number of significant figures is really what we're looking for in that particular example. Any questions on that there? Do you need to show all this? The answer is no. You don't need to show the equalities. You don't need to show the conversion factors. You're more than welcome to if it helps you to do so. But to get full credit on a question, everything down here you need to show. Yeah. So you need to show the dimensional analysis, the setup with the conversion factors, the units, the answer to a proper number of significant figures, and units associated with it. If the rest of the stuff above there helps you, do it, but you don't necessarily have to show it for credit. That. Any questions? All right, let's try a few more here. An antibiotic doses of 500 milligrams is ordered. If the antibiotic is supplied in liquid form, 250 milligrams in 5 milliliters, how many milliliters would be given? So take a moment and see what you come up with here. we're given 500 milligrams. And as I was talking about earlier, in this particular case, we're actually given a conversion factor in words, which happens a lot in sort of problems. We have 250 milligrams in 5 milliliters. We could use it like it's written there, or if we needed to, we could flip it around and put the milliliters up on top and the milligrams on the bottom in this particular case. And we have 500 milligrams. So again, we're going to set it up dimensional analysis here. 500 milligrams. Again, it is basically over 1, so the milligrams are on top. Makes my decision making pretty simple. I just need to use the one here on the right since it's in the opposite location. We want to get rid of the milligrams. So we'll go 250 milligrams on the bottom, a little 5.0 milliliters up on top. Milligrams divided by milligrams will give us milliliters left over. Multiplying there and dividing. So we're going to take 500 times 5 divided by a 250. Going to give me 10 milliliters in this particular case. First off, any questions on the calculation there? So again, sometimes we do see some conversion factors given to us in the problem that we need to use. We need to look at significant figures. Should I worry about the significant figures in this conversion factor? The answer is yes in this case because it was given to us in the problem specific for this problem. And it's not always going to be, say, medicine given to you in 250 milligrams per 5 milliliters, right? So that's kind of specific here. So this has 2 significant figures. This has 2 significant figures. This guy's got 3 significant figures. Here, 2 looks like a winner. So we do need to put a decimal, for example. We could also have done scientific notation 1.0 times 10 to the 1. Could I put a 0 after the decimal point there and wrote 10.0? Would that have been good? That wouldn't have been because I would have how many significant figures now? Would have 3, right? So too many. So again, as we talked about last time, adding extra zeros is not always the best deal either, right? So you got to make sure you get to the right one. Any questions on that one there? All right, let's try a couple more here, perhaps. All right, during surgery, a patient receives 5 pints of plasma. How many milliliters were they given? So take a moment there, see what you come up with, set it up, dimensional analysis, use some conversion factors. Okay, so let's take a look here again. We have pints. We ultimately want to get to milliliters. So one pathway again is pints to quarts, and then we could take our quarts to milliliters using our conversions here. These are our equalities that will do us, and again, are allow us to do that. And we have our conversion factors that we could get. Here again, we're going to start with what was given to us, which is 5 pints. Once again, we're going to go pints to quarts, and pints are up on top. So once again, we're just going to simplify it and go opposite location to cancel. 1 quart up on top, 2 pints on the bottom. That is going to get rid of our pints. If we stopped right here on the calculation, we could clearly see the way that we set it up. That quarts are up on top. And again, that makes it super simple to figure out the rest of it. I want to get rid of quarts, so now we can go opposite. So I need it on the bottom. Out of my 2 choices here, that has quarts on the bottom. So that would be the one that we want to use. And 946 milliliters up on top, a quart on the bottom. The quarts here will cancel. That's going to leave us milliliters as the only unit left standing up on top, which is good because that's what we want to end up with. We're going to multiply here. And again, we're going to come back and divide by whatever is on the bottom. So again, multiplying and dividing, pretty much all we're doing. 5 times 946 divided by, looks like only 2, I think, in this case. And that's going to give us a number here of 2365 milliliters. First off, any questions on the setup or the calculation there? We do need to look at some sig figs here to make sure we end up where we want to be. So should I worry about this conversion? The answer is yes. It's one of those ones in the last column there, metric to US. Here we have a 1, which we're not going to worry about, but this will contribute 3 significant figures. This is a exact conversion, so we don't have to worry about it. Over here, this guy has 2 significant figures, so it does look like 2 is going to be our winning sig figs in terms of lowest. That would bring us here. So that's going to give us a 2,400 milliliters, no decimal point. Or again, you could do a little scientific notation with not too many zeros, right? Why would I not want to write 2.400 times 10 to the 3 in this case? How many significant figures would it have if I put 2.400? It would be 4, right? Again, written in scientific notation, all the numbers before the times 10 part are important. That is, again, why we dropped the zeros there when we wrote it in scientific notation. Could I drop the zeros here and just write 24 milliliters? We cannot. It is the right number of significant figures, but big difference between 24 and 2,400, right? So we changed the meaning of it. So in sort of decimal form there, we need the zeros to maintain what it means. In scientific notation, we do need to get rid of it, so we don't have too many significant figures. Any questions on that one there? All right, let's take a look at one more here, perhaps. You are stranded 125 miles away from home and you decide, why not? Seems like a nice day. Let's take a walk. And you walk on an average of 55 feet per minute. How many days is this going to take you to get home? A few qualities there to use. Okay, so let's take a look, see how you're doing. So we got a couple things. We have obviously a distance we're traveling. We are given actually a conversion factor here, which is a rate. A rate, right, is like distance over time. So that's what we're going to use to kind of convert from distance into time, because we ultimately want to end up in days, which is a unit of time. We could have it at 55 feet per minute. We could also flip it around if we needed to. In a minute, you would be walking 55 feet. We have several equalities there to allow us to get to where we need to be. We do have a little situation here in terms of units. My units of length or distance is miles there, but feet there, which means I cannot use them together that way. I do need to do some type of conversion. Either I need to convert the feet to miles or the miles to feet, but I can't use them the way they are. I'm going to choose to convert my miles to feet. You could again do the other way and convert the feet into miles if you wanted to. So I'm going to go 125 miles, and I want to get rid of miles and end up with feet. Again, convert dimensional analysis here. We'll use our conversion. We want to go opposite, so 1 mile on the bottom, 5,280 feet up on top. Miles will cancel. And that's going to give us something like 660,000, I think, feet. All right. All right. So now we can use that with our 55 feet per minute as a conversion factor. And again, we can use it like that, or minutes on top, 55 feet on the bottom there. And again, we're just going to continue on. And our feet are on top, which means we do want our feet to be on the bottom, which would be this guy right there. So we're going to go 55 feet per minute. At this point, that rate is going to turn our distance into time, which would give us minutes. And we can now see, because we set up a dimensional analysis, minutes are on top. So we do want to go here with 60 minutes is 1 hour. Minutes will cancel. We also want to go with only 24 hours in a day, not stick to T like people like to do for some reason. So 24 hours on the bottom and a day up on top. Hours will cancel, right? So remember, 60 seconds in a minute, 60 minutes in an hour, only 24 hours in a day, not 60. People do that all the time on exams. So we're going to take our 660,000. We're going to basically multiply it by 1 on top. There's not really much to multiply. We're going to hit equals. We're going to divide by 55, hit equals. Divide by 60, hit equals. Divide by 24 on the bottom, hit equals. So again, I will divide equals. Divide equals. Yeah, you will get the right answer. It is 8.333, a bunch of threes. Yeah. First off, any questions on the setup here? Sig fig wise, when we look at it, this we don't have to worry about. Exact. This conversion factor that we did get from the problem, we do need to look at, and we would look at the 55 part of it. This has 3 significant figures. We would also look at our original number. Was this our original number? No, this was, right? And this one has how many significant figures? 3 sig figs. Although we used our entire number here because we talked about not rounding until the end. Technically speaking, if we wrote this number correctly, it should actually have 3 significant figures, right? It doesn't, but it should have 3 significant figures. And that means that when we get to our final sort of evaluation, we should actually end up with 3 significant figures, not 2 in this case. Any question on that? So it's also a really important point that, again, we talked about not rounding to the very end, but you do need to keep track of it, where significant figures are. Again, you don't want to just look back at this number and go, oh, there's only 2, because you might not have wrote it with the correct number of significant figures. You want to think about where that number came from, which obviously is 3 in this particular case. Any questions on that there?